How's it going, everyone? Welcome, Eulier Gonzalez here again. And in today's video, I just want to now dive deep into this concept of unioning and narrowing in Typescript. So the idea behind this is anytime that you need in your systems to extend or to enhance the applications, right? So because with JavaScript, you can do that by building is this rapid prototyping. But as you need to build now scalable applications where there is a ton of people involved, that so you need to somehow find a way to first understand the data flow. So the annotations of this shape or the values in your programs are clearly there, and also that your errors might happen is at build time, not at runtime. So because over the past couple videos and days, I went through describing is what TypeScript it is, and this is a subset of JavaScript that initially start as a project that Microsoft from a bunch of Microsoft engineers where they need to find a way to maintain these web applications. And given their previous experience with C Sharp, where this is a something that's a language that I really love, but because of this static typing. All right, so you can see what is the type of these different components or the program. All right, and this is known, or this was known as the script, sharp script, or yeah, sharp script sharp. Sorry, that was the original name of TypeScript, the predecessor of TypeScript. And then, well, now we are here to now understand what TypeScript fits into the web development. So remember, JavaScript is great for building rapid prototypes, but when it comes to now provide maintainability to those prototypes or MVP, so now things becomes quite, at least at enterprise scale, quite hard to deal with. So this is why when you go now and use TypeScript, which has now a compiling phase, which is analyzing is your code for error, which is something that compiler language does, right? JavaScript right now at this moment in 2026, the observable behavior is it behaves like a compiler when analyzing the code, not when it produces it. This is why we have things like syntax errors, early errors, and hoisting. All right. So, but the thing here with TypeScript is this is now a subset of JavaScript. I also look at how can we use this, how can we integrate, what are the prerequisites to use now TypeScript, whether it is that you need a Visual Studio Code editor, in our case VS Code, an ID, and now the compilers. So after I went through that and understand also how now it fits into the web development, particularly on the front end side, it is that you need to define your compiler, which is a library. In there, you set the configurations about what is the different target that you want to return, what is AKA the JavaScript output of this, and the different specific JavaScript engine versions. And also is where do you want to output this, or if you don't want to do that, and the watch mode. I mentioned is just the most common use cases of TypeScript, right? And as we explore now is at the basic typings, right? Which is part of the section, right? Or yeah, TypeScript in the build process, as I mentioned here. So how does it fit now in the web development using now Vite, and how convenient is for us to use now things like TSX to run some migration for that. And then as I look at the basic type annotation or the essential type annotations by exploring is that how you do that with your basic types and for functions and parameters. Past annotating is default values, optional values, and also working with these primitive values. Determining is the type of a value using the type of, right? Also, how you can now annotate is objects and arrays, and how you can combine those objects and array. Also, how you can type is key collections like map and set, something that we're going to see that later on, and the different caveats of this, and how you also do that with tuples, uh, the any type, the function types, and how you now define is the event listeners here by passing is a callback to an event listener, right? And so yeah, the typing with the event listener, and typing with JSON parsing, and typing with fetch API, right? So this is just the basics according to Matt Pocock, right? A software engineer that previously worked at Vercel and now he's currently devoted to this. So, and then in terms of understanding now how to leverage is the tools provided by the IDE. So, for example, is the so understanding uh, or how to read is the statements and how to hover on these different elements. So what are the introspections that we can get from these statements, and understanding this quick fix menu, what are the things that allow us to do, right? And also um, how you can now is depend on the selecting target, what are the options that this quick fix can give it to you, and how to trigger this quick fix menu, hitting the window or command dot. How you can also now triggering the autocomplete feature in your ID, which is fantastic. Let me say that, right? And what are the different approach on error in Typescript? Whether it's you now tell you the where the error is, or is quite indirected, or sometimes the error happening is at runtime, right? But most of the time, this is the kind of error of how you can actually, or how now Typescript actually is um, highlight those kind of errors, right? So whether if you calling an object, then you extend that property without properly annotating that, so you're not explicit about the annotation, so it might it is an error that it will throw, or sometimes the error is telling you explicitly what it is, or sometimes it's quite indirect in explaining that. And as I mentioned before, when you select your targets, so this will give you now some options that you can go with, right? And I do find them very powerful at as well. And also how you can refactor your code by exploring is the symbols, and how you can navigate the symbols and look at what is doing this kind of stuff over and over and over, and then you say, all right, now this is what it's gonna do. This is exactly what we are going to do. Yeah, this is exactly what we're going to do here, right? So yeah, this is the Typescript approach to errors and quick renaming in Visual Studio Code, and the also is the go-to definitions. So when you highlight or when you put your mouse over that, it will give you is not only the definition but also the different place where this function is called in your code base, which is tremendous. if you find yourself in doing a refactor. Absolutely. Absolutely. Also, you can now import several of these or your functions, right? How you can organize your files import or your import files alphabetically, or you can do a quick refactoring here, and some of the autocode formatting with prettier, and sometimes you need to restart is the server in the middle. So this is just to describe is the ID or this integrated development environments, the superpowers. So what are the things that the um, in our case Visual Studio Code allow us to go with? So the ability to do some introspection at the statement syntax or at the statement level, and then from there explore now about is what this statement is doing, and uh, give you now some or the ability to introspect this different or the anatomy of an statement, whether it's by a property or a function, or this is a class, or this is now an interface, and also allow you to have access to the quick menu anytime that you find yourself or the Typescript now detect an error, how Typescript actually detect those errors by running a Typescript server, and anytime a file change or you open a file, it's going to analyze that code and highlight with a red line those areas that needs that there are some errors. And once you fix that, it's going to analyze your file again, and if there is no error, boom. So your file is ready to be delivered, right? And also how to explore now is the IntelliSense. How useful is for us with the IntelliSense not only to look at where the code is, but also go to the definitions and where are the different places in our code base where we can see when this code is being called, which is tremendous. Absolutely, it's tremendous. It's tremendous, completely, bro. It's tremendous. It's tremendous. Um, well, the different Typescript approach to errors, whether it's by being explicit about or sometimes indirect, or sometimes the error is not quite visible. And offering is the ability to organize your imports sorted alphabetically, this autocode formatting, and the ability to restart the Typescript server. So this is just to understand this, how can I leverage them? But now, where the real deal is with Typescript, is about the unions and the narrowings. So on the unions, we look first at the important to understand the statement as it is, the heuristic of each one of those statements that we're writing, and particularly with the null property, and what the null property is, and how you can now identify is the null property in your code. So by combining is different type, or by declaring different types in exercise like the HTTP codes, where you want is to now identify specific codes for success or error, and when you find yourself in the need to combine those two set of types into one bigger, the idea here is that anytime that you find yourself in the need to represent enhancements in your code base, so you do need to find, or you know how to do that by using types and by using unions and also narrowing, but particularly this notion of widening and narrowing, right? To represent now is the different and or the ever evolving nature in the business. So this is what Typescript here allow us to represent, right? It's this different type of data in our systems that sometimes might be one, and 6 months later it can be a different, or it can be enhanced, some of that structure here. So that's good. I also explore how to do that with, again, using is now these union types, defining type literals with unions in parameters as function, all right, and how you can also is use those in our code, looking at how big can a union type, all right, so how big can a union be, and that is, well, so what is the most common, so what yeah, how big can a union be, all right, and also exploring is the literal types for wider types. And when it comes to narrowing, using whether it's a type of to check for that, or the conditional narrowing in Typescript here, in this conditional narrowing type is to say, hey, this is the particular way if I don't know what is the date at that moment, or if the shape of this data will change based on a particular condition. So for example, API calls, right? And I do find myself in the need to express those scenarios. So I need to write some tests to actually express in those cases those scenarios. So resolving literal with wider types is one way to do that. Narrowing using type of, the conditional narrowing here. And also when it comes to use now Boolean, this is something that sometimes won't work as expected. How also can we narrowing using is map in Typescript, and because Typescript doesn't know is the shape of that map internally, it is preferred to actually is extract that data and then do the checking there, right? Again, it is due the dynamic nature of this map, right? And the same for sets, all right? How you can now is narrowing your code by throwing its early errors, which is great, all right? Narrowing in statements. So for example, if you find yourself exploring as an object that you don't know the shape right now with unknown, okay? So you can use now the imp to actually verify that data actually exists, right? The other is introducing the unknown type in Typescript, which is something that I actually mentioned. And this unknown type is this umbrella terms where now all the different type are assignable to. How you can actually deal with unknown error in Typescript. Exactly, unknown errors in Typescript. So for example, like that, whether it's by using as the instance of is a good example. Narrowing unknown in large conditional statement, which is pretty quite interesting. What is the never type here? And never is something that can never happen, or it will never happen. So sometimes when you throw now an error, the code right after that will never be called. And not to mention that this function will never return something. And how to now solve this never types in arrays, for example, right? This is quite interesting here. So narrowing return types in Typescript. So
in this exercise, we have a throw error function. And this throw error function takes in a message here and throws the error. It's also been given a return type of undefined here. So this function kind of returns undefined, or at least this is what this is saying. And we have a handle search params function here. The handle search params takes in a params, which is ID of string, or it might be an ID of string. And then we're saying const ID equals params ID, or throw an error, no ID provided. And what we're doing here is inside this ID is now string or undefined inside this handle search params function. And we're trying to get this ID into a spot where it's actually narrowed down to string. Because if you think about it, we've got one branch here, which is the params.id. And if params.id is defined, then it's going to be string. So ID will end up being string. Great. If it's not defined, or if it's a falsy value, which is what this OR symbol is doing, then we're going to throw an error. We're going to run this piece of code, throw new error message, and it's going to throw an error with no ID provided. So in theory, this ID here should be just string instead of string or undefined. So your job actually is not to change any of the code inside handle search params, it's to change some code inside throw error, inside this function here. And see what you can come up with and see if you can find a better type definition for throw error, which actually makes this happen. Good luck.
I get it. I get it. I get it. So the thing here is that because in this ID, and we're talking about assignability here, the assignability of this notion of wideness and narrowness, right? Wideness and narrowness. Wideness and narrowness. Right? This is the notion here. To say, hey, yes. So if I'm here, right, this can be either exists, okay, because I'm passing is now a string that is identifier, or not here. So the thing here is that this function is somehow is returning is now something, and this particular pattern is quite useful when you see or when you find yourself in the need of throwing an error here. Hey, do we have do we have this property? And if it is, good. And if it's not, throw this error here.
Okay, so the reason that this whole setup doesn't really work is because of this undefined type annotation here, which is on the return type of the throw error function. If we think about it, we're not actually returning undefined from this function. If we were to return undefined like this, then this function would make more sense. The throw new error would never be hit, and you can see that because it's slightly grayed out. And I think it's, you can hover over it and see unreachable code detected. And now the ID would actually be a result of the throw error function, which doesn't throw an error anymore, it just returns undefined. So the ID, now string or undefined, that makes sense. And you notice though, we can actually delete that completely and maybe add never on instead, because never is actually the thing that this function is returning, right? It's never ever returning. So now what happens when never is included in, like, let's say you have a type example equals string or never, we can see that example is only string, because never in that situation kind of like is assignable to string, and so it sort of melds itself out of the union. It removes itself from the union. So you end up with just string there. So we have string, params ID could result in a string, or it could result in never, meaning that ID is typed as string. And this pattern is super duper useful because it means that Typescript can, like, throwing an error in situ right here, like in the space where a value might be, can actually mean that you get really nice autocomplete. And this is a nice pattern. I recommend you take note of it. But you notice too the return type on our throw error function. This can actually lie to us pretty badly. We can have like a string inside here, like an object, and our throw error function won't actually like error. And that's because never is assignable to anything. That's why it works. And when you kind of combine it with a string, it removes itself from the union because it's assignable to string. And so this return type can lie quite badly to us. You'll notice though, in the second solution, that we can actually just omit it completely. And when we do omit it, then throw error just returns never. And that's what Typescript infers here. And that is really, really nice, because it means that first of all, we've got one less annotation to worry about. Second of all, if we ever kind of make a change to this, then that'll ripple out in the rest of our code base. And thirdly, it just gets it correct. So this is, I think, an interesting argument for maybe not using implicit return types in your code. In this exercise, we have a function called findUsersByName. We have a search params object being passed in, where we have some search params which might contain a name string. Next, we have some users, which is an array of objects which each contain ID and name. We're passing both of those into the same function. We're first of all checking if there is a search params.name, and if there is, we're returning users.filter, and then inside that filter, we're checking if the username includes search params.name. And then if we don't get a search params.name, we're just returning the users. Inside our test below, we've got some findUsersByName. We're checking for the name Bob, and we're expecting the users to be filtered out into ID1 and name Bob. Now, there's an issue here, and the issue is inside our filter function, username.include search params.name is erroring for us. It's saying argument of type string or undefined is not assignable to parameter of type string. That's really weird because we're narrowing search params.name here. Why wouldn't it also be narrowed here? That's interesting. So your job is to try to figure out why this is happening and see if you can kind of work with TypeScript a little bit, find another way to write this code where this error goes away, but the behavior is preserved. So don't change any of the type definitions up here. We're just changing the stuff inside the function body.
So here it's say, hey, this is the search param names. If that exists, that it might be even undefined. Here, in here, it say, hey, despite that, by the time that I'm evaluating is this here, which is quite interesting, right? So by the time that I'm evaluating is these things here, look at this. Look at what this thing is doing, or is telling us. It say, hey, even though this search pattern here, despite that we actually narrowing down, is actually asking that ourselves here, right? Shouldn't this be now actually search pattern.name, right? So it turns out that so not only this, but also that we need to do something like this, right? So it's like the name here. Okay. So what I have to do is to have to see is, hey, if this exists and the search pattern dot name, the type of this, right, is equal to a string. And in this case, now I'm saying, hey, I'm narrowing this, right? Not only that I'm checking that that thing exists, all right, or the search pattern name, but also is that the search pattern type must be a string. And it still have this. It say, hey, argument of type assignable is not assignable to a type string. The type undefined is not assignable to type string here. It say, or it reads this. So somehow now at this moment we have a something like this, you know. It's like at this moment we have something like this, right? And this is part of the error here. It's like, shouldn't be now here at this point is search pattern.name already is a string, right? So in this case, so now that we are sure that this actually exists, we can store that data here into name, right? And then you do something like this with name. And that's quite interesting, you know. That's and let's evaluate here this. So what I'm doing is now I'm passing is a search pattern here. That at this point now this is an a string, right? But it turns out that if I pass this here, right, the compiler say no, I cannot recognize that, all right, and give it and pass it to you here. That is quite interesting. If I look at this, it say now this is a string for that. So this compiler is quite weird here. And again, search pattern at the end of the day is an object that might or not have that property. So here what I'm doing is narrowing down, and if that property exists, I'm going to have this. And again, what we're doing here is just to define as a scope, all right? And I'm defining as a scope because now our using is now a cons of name, and any time that cons or let are defined inside of a block statement here, it create by default is a scope. And here I'm calling is this function called filter, where now I am passing is this function's reference, all right, to the filter. So anytime that these users are called, and anytime that the filter method is calling on these collections, this is the function that is going to be executed. This is the callback that is going to be executed. And since now, so you have now some trouble here. It seems like you have now some trouble here. So Typescript has some trouble here when we're narrowing things like this, you know? When narrowing things like this.
Let's start this explanation by examining all of the different scopes there are in this file. And scopes are a JavaScript concept, not a TypeScript concept. So we have the module scope, right? If I were to declare something inside here, const example equals 123, then example is declared within the module scope, the scope of the module. If this wasn't a module, if it was a script instead, then this would be in the global scope. But because we've got imports and exports, it's a module, so we've got something in the module scope. So find users by name, that's a function declared in the module scope, and it has its own function body, which is its own scope, right? We can declare a variable inside here, const example equals 123, and then we can't access example outside here, right? They're not in the same scope. So, great. We've then got another scope inside here, inside this if statement. Wonderful. And then another scope inside the function body. So actually I can make this clearer by adding some curly braces and in return like this. Now scopes have an impact on how TypeScript handles narrowing in certain cases. So what we have here is inside the if statement. You notice that before, when we've tackled narrowing, we understand that searchparams.name here, we can call to uppercase on it. And TypeScript will consider this safe because we've checked if searchparams.name exists, right? It's not undefined. And so we're safe to call uppercase on it because it's never going to be undefined. But if we move it into the upper scope where we haven't done that check, no way, right? It could be undefined, absolutely. But then if we move it even to a function scope inside here, it becomes all undefined again. What? How is that possible? How is that possible? Well, what's happening here is that .filter, right? We're passing a function to it. Now we happen to know as JavaScript developers that filter is called synchronously, right? It's just called filter, 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 filter like that. There's no gap in between where searchparams.name might be mutated or changed or things like this. So .filter, right? It's synchronous call, but TypeScript doesn't know that, and there's no way to annotate that. Filter could be a function that's like a subscribe function, like add event listener, that's called at a later date when searchparams.name might have been modified by something else. So TypeScript can't know that inside this if statement right? That everything below that is going to be not undefined. So how do we solve this? Well, one way to do it is we can save it to a variable. We can say const name equals searchparams.name. Now, and if we take name and we put it inside here, now it starts working. Look at this. So const name equals searchparams.name. The reason this works is fairly easy to understand. Name is never going to be mutated because it's saved in a const. So this means that filter function is pretty safe to assume that name is always going to be the same thing, and name is considered a string. This means in this scope, so the if statement scope, and in the function scope below it, it's always going to be a string. What if we change it to a let? Well, let happens to work too because TypeScript actually tracks whether you've assigned something to a let. This actually happens since TypeScript 5.5, which is why I'm wearing a different outfit from the problem setup. So now name, like this, if we were to reassign it, we can say name equals undefined. Yet now TypeScript has tracked that we're assigning it to be undefined, and it actually tracks that it could be undefined in this spot. Same as if we put it inside here. What if I do it as a string? Yeah, it tracks that too. So TypeScript has actually gotten a bit smarter here since I first recorded this exercise. So the way you get around this narrowing in different scopes is you save it into a variable. And that might feel a little bit awkward. Why can't TypeScript actually track like object properties in the same way that it does variables? Well, object properties can do slightly crazier things. You can have getters inside them that you can't have in variables. And so TypeScript tends to trust these properties a little bit less than it does just with pure variables. So if you're having this kind of issue where you have narrowing in different scopes and everything's going wrong, then save it into a variable, either a const or a let, and the errors will magically disappear. Look at that.
Especially if you're, but the problem is of this dynamic nature of property accessors. Especially property accessors that are not there.
Let's imagine that we have two functions that do very, very similar things. We have join names here, which takes in a value which is unknown. This could be a value coming from anywhere, coming from search params, coming from user input. And it checks to see if it's an array, first of all. Then it checks to see if every single item is a string inside there. And then if this works, then it joins them all together. We also have something that has pretty much the same logic in creates sections, which takes in a value of unknown, does the same check, array.isArray, checks every single item, and then maps over it and basically maps it with a section, so reformats the text. We've got some tests making sure they behave as expected, and there's no errors in this file. But there's a bit of duplication happening here. We can see it just here. This duplication is a little bit awkward because we've got two pieces of logic that look exactly the same. Why not create a reusable type guard to basically grab that logic and just put it in a function somewhere so we can reuse it hundreds of times? That's your job, is to make sure everything keeps passing here, but we refactor it out to its own function to see if we can just reduce some of this duplication. Good luck.
No, but here, who can help me here is by say type join name, create section, type okay, this is part of the genetics here. Type guards here.
The solution here is amazingly simple. This used to be a much more complicated problem to solve, but since TypeScript 5.5, which as of time of recording is just been released, we can now do this. I can just copy this logic into here. I can say const is array of strings, and then I'll just return this value here. Obviously we're getting some errors because value is not defined, so let's define it here, saying value is of type unknown. And now I can just replace the logic inside here and just say is array of strings, calling it on value. and it works. Now this is amazing to me. I mean, to you watching this in the future, this might not be so amazing because TypeScript will have had this for a while. But what's happening here is if we hover over is array of strings here, then you can see that we have the function parameter just there. In fact, I'll zoom in a touch. And we have a return type here, which looks very interesting. We have value unknown as the parameter, and the return type is value is string array. This is what's called a type predicate. And type predicates are something which are quite advanced in TypeScript. We will look at them, I think probably in maybe the last chapter of this. And what's going on here is that TypeScript is inferring the fact that we're returning this logic inside here. We're doing some narrowing inside there. And it's inferring the fact that this function, when it returns true, will mean that value is inferred as an array of strings. So when we call it on here like this, it means that value is an array of strings. If we were to do the reverse, if we'd say it's not an array of strings, then value inside here would still be unknown. But outside of those brackets, value would be an array of strings. So it's like we're able to recapture some of this narrowing logic, put it inside a function, and it just works. You are, of course, allowed to add your own to here. And actually, one thing you'll notice is if you add a return type here, if you add Boolean as the return type, then everything actually stops working. If we hover over this, we can see value unknown returns a Boolean. And because it's not returning any special awareness of what value is supposed to be here, it means that value is still unknown here. So this is a good argument for actually not annotating your return types, because if you're adding this interesting narrowing logic here, then your function is going to be automatically inferred as a type guard. Really, really clever stuff.
Okay. Reusable types guard. Oh,
in this exercise, we have a type called shape. And this shape type has a kind attribute, which is a string, which is always defined.
Okay, so I'm gonna leave this as it is. Bye-bye. And I'm back. All right, so let's take a look at this particular thing of handling separate but related types. So let's get into this.
In this exercise, we have a type called shape. And this shape type has a kind attribute, which is a string, which is always defined. And then we have a radius, which is possibly defined and is a number. And then side length, which is also maybe defined and is a number. Then we have a calculate area function below. This calculate area function takes in a shape, which is a type shape. And we say if shape.kind equals circle, then we return math.py times the radii, and then we're good to go. We're off to the races. And then otherwise, if it's a shape.side length, we assume it's a rectangle instead, and then we just times the shape.side length times shape.side length. So you can imagine this is a kind of polymorphic function which takes in two separate shapes. And
talking about polymorphic functions that take in two different shapes. Okay, it's a polymorphic function that take in two different shapes to handle those text. Okay.
And we've got some tests down below. We're expecting the test to pass if we calculate the area of the circle correctly. So this type annotation, though, is really bugging me, because we can actually pass in a bunch of illegal stuff into here. We can say calculate area, and we can pass in like kind. We can first of all pass in like a kind that doesn't exist. We can give both a radius and a side length, which just should not be possible. There must be a better way that we can express this logic. So I'll give you a clue. In fact, I'll give you two words. Discriminated unions is the thing you need to look up. And by doing that, you're going to discover a really interesting way to describe this shape property. It's going to use the union symbol that we've covered before, and it's going to also test your knowledge of narrowing as well. Good luck.
Let me go with these two last examples here. One of them is narrowing in different scopes. All right, because it seems that Typescript is not well aware to scoping in different, so scoping variable or passing variable, or is when you're working with objects properties, in different scopes. So TypeScript doesn't like that. And so not only that it doesn't like that, it prefers to hold is the value or a reference for that object. This is narrowing in different scope. And why we have to pass this? The reasoning behind this is quite unclear, but I mean the TLDR is that TypeScript says, hey, this is what I need you to pass me as a new identifier, and then I can have access to. Because somehow, if you want to use this dot notation, it is interesting. Okay, things are starting to make quite sense here. So JavaScript doesn't, or TypeScript doesn't like things that are not defined. So TypeScript doesn't like possible things, because if I do things like this, okay, it doesn't matter. But when you're talking about now is optional properties or optional values in objects, TypeScript doesn't like that, and it say, hey, I prefer to is extract this logic here into its own. Let's say your name into its own identifier, right? That actually contains is a value. Why is that? Because now TypeScript say, hey, I do know what this value is, right? I can, okay. So I can narrow down this into a primitive or into a known value, right? Into a known type. This is interesting. Why is doing this, especially scoping or narrowing in different scope when using these optional properties, right? Again, because TypeScript needs is things that are be there, present things. So it prefers to give now. Yeah, it prefers to give. So it prefers now. So it doesn't like the dot notation in objects that much. Despite that we're actually passing that, it prefers that to hold that value into its own identifier, and then work with that. Mm-hmm. The other is reusable type guards.
Let's imagine that we have two functions that do very, very similar things. We have join names here, which takes in a value which is unknown. This could be a value coming from anywhere, coming from search params, coming from user input. And it checks to see if it's an array, first of all. Then it checks to see if every single item is a string inside there. And then if this works, then it joins them all together. We also have something that has pretty much the same logic in creates sections, which takes in a value of unknown, does the same check, array.isArray, checks every single item, and then maps over it, and basically maps it with a section, so reformats the text. We've got some tests making sure they behave as expected, and there's no errors in this file. But there's a bit of duplication happening here. We can see it just here. This duplication is a little bit awkward because we've got two pieces of logic that look exactly the same. Why not create a reusable type guard to basically grab that logic and just put it in a function somewhere so we can reuse it hundreds of times? That's your job, is to make sure everything keeps passing here, but we refactor it out to its own function to see if we can just reduce some of this duplication. Good luck.
Okay, now I see this reusable type guards. So what we're doing here with this piece of logic is to not only abstract it into its own function to say, hey, I'm going to say is array string, right? It's a string array. It's a string array, right? And here I'm going to compute this. But what I'm gonna do is to giving this passing this value, I want you to return is this. And look at this. Let's go to evaluate this one by one. So here's a constructor, or this, yeah, constructor object of the array that it say, hey, let me check if this value that I'm passing here contains now is an array. And how it determines that? That's a good question. Well, by exploring into the prototype if that contain is the length property, right? So for example, this is the declaration, check if the passed value is an array, and it performs a branded check similar to the in operator for private fields initialized by the array constructor. It is a more robust alternative to instance of array because it avoids false positive and false negative. So array.isArray reject values that are in actual array instance, even if they have array.prototype in the prototype chain. That's interesting, because with instance of, we'll accept this as it does check the prototype change. So with the instance of is looking at the prototype change, but with the isArray does not. It say accept an array constructor in another realm. Instance of array return false for this because the identity of the array constructor is different across realm. See this article to determine with absolute accuracy whether or not JavaScript object is an array. So unlike the instance of, that is gonna check if this is the if the prototype is an array, all right, along the prototype change, holy hell, determine with absolute accuracy whether or not JavaScript object is an array. Look at this. This is the MIT. Typing problems in JavaScript. JavaScript types of operator is well known to have confusing behavior with type null equal to object and type null is different to null. This mistake trip up newcomers, and even so often it will trip up seasoning yet forgetful veterans. But we have basically grown used to it. Perhaps more important, there is a fail safe. There is a fail safe, a workaround. Simply compare directly the v equal to null instead of the type, right? To eliminate null from the possibility under consideration. So if this value that I'm receiving is equal to this primitive, all right, and determine whether a value is an array. Typing problems in JavaScript. Okay. So the type null is equal to the objects is perhaps the most common typing mistake in JavaScript, but there are others as well. As much less common, but not less confusing problem is that of determining whether an object is a collection as an array. Surely say you, this is a simple problem with a simple solution like so, right? If this object is an instance of array, oh, fabulous job. Under certain circumstances, the above code is perfectly functional. Considering the history of the web, it is not surprising the issue wasn't quickly apparent. The problem arises when one's considering an aspect of JavaScript in browsers not contemplated by ECMAScript multiple globals. The problem arises when one considers an aspect of JavaScript in browsers not contemplated by ECMAScript. The problem arises when one considers an aspect of JavaScript in browsers not contemplated by ECMAScript multiple globals. Multiple globals. What the French does is this? Yeah, but the problems arise when one's consider an aspect of JavaScript in browsers not contemplated by ECMAScript multiple globals. The ECMAScript specifications describe the environments and mechanisms. The environments and mechanisms involved in executing a string of code. The syntax and basic semantics of language constructs are certainly important, but without the built-in methods and object coding in Java in ECMAScript wouldn't be much fun. These methods and objects are accessed through the global objects, exactly through this realm. And it is here where things go astray. Oh my god. The ECMAScript 3 environments implicitly assume the existence of a single global, or perhaps of islands, each of within its own environment, with no interaction between them, and does not in any manner address the idea of multiple globals. Multiple global, however, are fundamentals to the browser. Each window object is the global object for the script its page contains or reference. What about arrays in different windows? They share mutations hazards. What about arrays in different windows, in different tabs? They share mutation hazards of having arrays in two coordinating windows be instances of the same array constructor. So sharing the same array.prototype is enormous when either page augmentates. Array.prototype, not to mention the security problems when one page is malicious. So array, okay. So whether it's you have one page, all right, and each one of those pages you have is different uh, data structure being used, particularly arrays, and if each one of them has their own arrays, right? So share mutation hazard of having arrays in two coordinating windows be instance of the same array coordinator, and sharing the same array prototype is enormous when either page augmented the array.prototype. So arrays and array prototype in each window must be different. Okay, so array and array prototype in each window must be different. Therefore, by the semantics of the instance of, the all instance array works correctly only if O is an array created by the page original array constructor, or equivalently by use of an array literal in that page. And there are any other methods of determining whether a value is an array that might work around this. Like the O constructor is equal to array is one with the same problem as an instance of check. Another option rely on so-called doc typing. What do you mean doc typing? Style of dynamic structural typing by lazy checking of object attributes. If it walks like a dog and it quacks like a dog, then it must be a dog. To determine whether an object can be used for a particular purpose, with nominative typing, an object is a given and it is declaring as such. With doc typings, an object is a given type. It has all the method properties required by that type. Doc typing may be viewed as usage-based structural equivalence between a given object and the requirement of a type. In some statistically typed language such as Boo and D, class type checking can be specified to occur at runtime rather than at compile time. C# can invoke dynamic typing, which behaves similar like doc typing, through the keyword dynamic. Why they call this doc typing? If an application is a doc test of abductive reasoning, is usually an expression. Whether an object can be used in a particular purpose. But this is doc typing. where if a value quacks or looks like an array, then it is an array. Okay. Along the constructor checking lines, you could check for other array method like push or concat, or perhaps for a lengthy property. But this property could exist in the same fashion of a non-array object. If you're willing to have a false positive and negative, assuming unconstrained inputs, that might be acceptable. But of course, that won't always be the case. One test in this style is object.prototype to string.call is equal to the object, which is an object. It's a stringified an object. Okay. So if I call this object, okay. So look at this. So if I do this, if I want to stringify or to coerce a string, right? That's interesting. Yeah, it converts that into an empty object. Even if I pass this, so here I'm just coercing is this object into a string. But it's interesting because object has this shape. But if I pass now an array, which supposed to be an object array, it doesn't. It just gives you an empty string. Oh my god. Here we go. But that relies on the object.prototype to string and function.prototype.call not being changed. Probably a good assumption, but still fragile. And it is also a bit more an obvious hack than any other idea. Enter array is array. So for these reasons, ECMAScript 5 defines a method called array.isArray to completely address these problems. The problem of verifying if that array is an array, all right? Not like dot typing. Oh, okay. Not assuming that. But it's because in the ECMAScript 3 environment implicitly assumes the existing of a single global. To completely address this problem, in this first argument provides an array to create in any window. And the same for this. This is currently cross window fail. Technically, the answer to this question is as soon as you want. The usual feature for array.isArray allows you to use this method if it exists and is ignored if it doesn't. You will be able to meaningfully use it. However, starting with Firefox here and take it. But this is interesting. I found this article helpful in examining some of the hacks to determine whether or not an object is most likely an array. No? Okay, it can load the site. So, oh my god. So the thing here. I'm gonna use Claude here to help me clarify this idea. Or the problem, which is this. So the problem is that ECMAScript 3 assumes there is only a global object. So mutating one array so mutating one array in one window, uh, so mutating one array in one window can also mutate the array in another, right? Of share mutation. If that any, it is that arrays in different windows are not shared, which breaks detection. Arrays in different windows are not shared. Here's the core problem. Each browser window has its own global objects. Okay. Exactly. Each window has its own global object, and therefore it is own array constructor, an array.prototype. This is actually intentional. If two windows share the same array.prototype, then one page augmentating or maliciously page tampering with it will affect the other. That will be a massive share mutation hazard and a security nightmare. But this separation creates a detection problem. Since each window has a different array constructor, exactly, since each window has a different array of constructor, right? Instance of arrays only return true for arrays created by the current window array. Holy hell. And an array created in an iframe or another window via new other window.array will fail the check, even though it is absolutely a real array. The same issue hits here. The constructor is equal to array. It is comparing against the local array, not the one that created the object. Before it exists, people resorted to hacks like this. Object.prototype to string.call is this. If I am calling this object and I stringify, okay. So look at this. So what it's doing is just to transform that, right? With the object the prototype, the object of prototype to string, all right? And let me call this. So if I pass now this, so this will give me now is a proper, as you can see, object as it is, whether it is an object or object array, right? But it's giving you the instance of, if I say use, so if I say now class user, and this user will be now is a constructor, right? I don't think constructor, right? I don't receive anything here, and I'm just going to do is pre-name, pre-name, and then I'm gonna give the name here. I'm gonna receive is the name here as a name, right? And I want to define this name as it is, right? And then I want to just console.log is this dot name, right? So if I now say something like this and define here a user here of the new user class function constructor, right? So if I say something like this, it will give me is now this is an object, right? But again, this color here, so this color here, it can actually determine is if this is an array or not. But again, this is going into this built-in objects here, which make it easy for us to check the type of this. Okay. even if I do something like this, right? It will give you now the, hey, this is a function, or hey, this is an array, or hey, this is now um, a, an object here. This is how you can actually hack your way into this, which works across Windows, but it is fragile. It breaks if someone's override to string or call. Duck typing approach like checking for push or .len produce false positive or non-array object, which is my intuition. So if I say, hey, if you have now this len property, or yeah, if you have, I get it why they call this duck typing. So if you walk like a dog and quack like a dog, so you're probably a dog, right? Okay, I get it. Yeah, this is why those dog typing approach can give you false positive. And the problem is that this arrays, right? Okay, the problem is that this arrays. Mm, all right. Okay. So the problem is that this array. Let me make a pause here. That was a lovely coffee, bro. Oh my god. That was a lovely coffee. But that is the problem here. But that is the problem. So that's the problem here with the arrays, is that arrays are different, is that array in different windows are not shared. Why this matter? Because browsers like Chrome treat each one of those window or tab as a process, aka they cannot share data like in a like if they were threads. All right. Okay. So each window, since each windows that represent a tab in browsers like Chrome. Okay, so each window that represents a tab in browsers like Chrome is a separate process. Okay. So objects like arrays defined in a window. So objects defined in a window, specifically on the heap. All right, are not shared across. Yeah, are not shared across tabs, right? So why do we want to detect that? Right? Well, because the problem is that each browser window has its own global object, right? And therefore, exactly. So since each window that represents a tab in a browser like Chrome is a separate process, objects like arrays, which are defined in their own realm, objects like arrays define, so objects like arrays, which are defined in the global object, all right, objects like arrays in a window specifically store on the heaps are not shared across tabs. So why this is important? Because sometimes, okay, so therefore it's an array, exactly. So therefore now each one of, so each, okay. So the problem is that each array, since is a and this is actually intentional. If two windows share the same array.prototype, there will be a massive shared mutation hazard on security. But this separation creates a detection problem. Since each window has a different array construction, it only returns true for arrays created in the current window. So the problem is that each window, each array is created exactly, is created so the problem is that each array is different in each windows. The problem is that each array is different in each windows. So an array that is created in an iframe or another window will fail the check. So the problem is that each array, so each newly created, or the problem is that newly created or new created arrays, and the problem is that the problem is that created array, or the created array is different in each window, right? So if an array is created as an iframe or in another window via the new other array, will fail check. So, but the problem is this separation of concern, and how do you make sure that that window actually? Okay. The problem is that the creating array is different in each window, and to verify if that in using instance of. Okay, the problem is the creating array is different in each window, and using instance of to check for it will be true if that array was created in that object, or in that window. Holy moly. Okay, so then we have this like dog typing scenarios where you say, hey, I do have now this array, and dog typing is like, if this quack like a dog and walk like a dog and shit like a dog, it probably is a dog, right? So, but this approach are this approach produce false positive of non-arrays. So, which is my my problem was like that. Is, hey, I am going to verify if you have now the length property or if you have the length property or the push or pop, so you might be an array, and some other object might implement that. So you cannot be sure if that is so 100% if that object is now an array. So EX6 solve this cleanly. It is an spec level check on the object's internal class. Now the exotic array behavior. So it returns true for array from any windows and false for everything else. No prototyping, chain walking, no dog typing, no fragility. That's interesting. So array dot is array. Okay, to summarize the ECMAScript 3 assumes one global. Browser have many, and the deliberate non-sharing array across window is what made reliable array detection impossible until array is dot array came along. But the problem is that so the language assumes one global. Browsers may have different globals, right? Even nested globals, like iframes, for example. In detecting if an array, in detecting if an array is, and detecting if an object is an array, it was based on the window that creates that array. So this is why they say, no, let's solve this, right? By defining this method called isArray, introducing ES5, and solve this cleanly. It's an spec level check on the object's internal class. All right, now the exotic array behavior. So it returns true for array for any windows and false for everything else. Okay, but that was a problem. The problem is and this is something that still is present, right? Mm-hmm. And window.open. Mm-hmm. So parent window has its own array construction on its heap. iframe has its own separate array construction on its heap. And iframe creates 1, 2, 3 and passes it to the parents. So the parent checks the iframe array instance of the array, and this walks the prototype chains looking for the parent's array.prototype and doesn't find it because the array prototype is the iframe. The array prototype is the iframe array.prototype and returns false. So the array.isArray bypass all of this by checking the object's internal spec level classification. So the TLDR of this, holy hell, holy moly. So the TLDR of this is use the isArray method. So when you're going to compare if this is an array, look for the array for that, and isArray here. So now that I understand the problem, let's go back to what we really care. You know? Let's go back to what we really care, and that is here. Right? Diggy is here. So this is what we're doing here, is that, hey, I do want us to now check for an array and do this particular problem that each window has its own arrays, and to check that using the instance of is going to look at the instance, it will look to the prototype change, or in other words, it will check for that global. So what we're using is array rather than instance of, because this will check now is the prototype change. And the problem with that is the TLDR is each one of those windows that represent a tabs, right, has its own global and therefore its own array. So any array that is created in that window or in that tab is exclusively to that. So if you want to now share an array to compare that to another window, it throw you a false positive. It say that no, I cannot. This is false. But again, this is because this separations of concerns, which improve the security, and the TLDR is anytime that you need to verify for an array, use the array construction, which is going to check at the class spec level. Okay. So hey, is this an array? This will return you a boolean. And this is gonna say, hey, not only that, I'm going to return you here, argument is any. That's interesting. Here, this is an array construction. Argument is any. And here, so not only that I verify that this is an array, and if it is, which is interesting, it's supposed to return is array. That's interesting. Is array should return is true or false. Look at this, right? But the thing here is, so the thing here, exactly. This is describing it. What is the problem? This. It works across realms. It works across global objects, across window objects, right? That's what they call realms. But again, the thing here is that okay. And this was determining. Holy moly! You should definitely know this, bro. Okay. So this supposed to return you is now a true or false, right? Return true if value is an array, otherwise false. False is always return is value if a type array instance. But again, here is telling you that this supposed to return is true, right? Okay, right? To return is true. Oh my god, what it is? They're supposed to return true. And here we are now actually iterate through all of these elements and check if these elements, if each one of them now is a string in this particular case. We're using the type of items equal to string here. Mm-hmm. All right. Okay. Okay. Is this one, right? Is this one. And here I'm gonna say, hey, if this is a string array, and I'm gonna pass the value here, right? And the same for this. But the interesting things, at least to me, is that not only that I abstract as the type guard, they call here type guard or reusable type guard. If I take a look here at the type guards, let me see, let me read about this type guard. So this is type guard. All right, type of type guards using narrowing here, type guards. Okay, it calls this like that, narrowing type of in type guards. Okay, all right. Okay, type guards here. They call it type guards. Okay. So as we have seen, JavaScript support a type of operator which can give us very basic information about the value we have at runtime. Typescript expects this to return a certain set of a string, which is the string that type of actually returns, right? And they call this type guards here. And they call is type guards. So in TypeScript, checking against the value returned by the type of is a type guard. Okay, 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 okay. So checking a value return. Okay, checking a value returned by the type of is a type guard because TypeScript encodes how type of operates at different levels. It knows about some of its quirk in JavaScript. For example, notice that in the list about, type of doesn't return the string null. Like this. String is possibly null because you only check for the object. And all the quirk in JavaScript, type guards. Okay, so checking against a value returned by the type of. A print function, we try to check if it's string, if it's an object, to see if it is an array type. Now might be a good time to reinforce that array are objects type in JavaScript. But it turns out that in JavaScript, type of null is actually object. Exactly. This is one of those unfortunately accidents of history. You will get used to that. Users with enough experience might not be surprised, but not everyone has run into this in JavaScript. Luckily, TypeScript let us know that string was only narrowing to string or null, instead of just a string of this. This might be a good segue into what we call truthiness checking. Okay, truthiness checking here. In JavaScript, constructs like if first coerce their conditions to Boolean, exactly, to make sense of them, and they choose to branch off this. So here is the possible falsy values, which is something that you can look at this spec, and all coerce to false, and other values get coerced to true, right? It is fairly popular to leverage this behavior, especially for guarding against values like null or undefined. Values like null or undefined, right? And you will notice that we have gotten rid of errors above by checking if the string is truthy. This at least prevents us from thread errors when we run our code like this. Type error null is not iterable. What the fuck? Okay. Exactly. Exactly. It's not an iterable. Exactly. Exactly, because it can be either a string or a collection of a string. Keep in mind that the truthiness checking of primitive can often be error prone. As an example, consider a different attempt at writing print at all. Don't do this, keep reading. We wrap the entire body of the function in a truth check, but this has a subtle down sound. We may no longer be handling the empty case correctly here. Right? If you go down here, so you're actually dealing that, but not the null case. TypeScript doesn't hurt us here at all, but this behavior is worth noting if you're less familiar with JavaScript. TypeScript can often help you catch bugs early on, but if you choose to do nothing with a value, there is only so much that it can do without being overly prescriptive. If you want, you can make sure you handle situations like this with a linter. One last word on narrowing by truthiness is that Boolean's negation with this filters out from the negated branch. Okay. So TypeScript prefer here is the operators rather than going with booleans here, and equality narrowing. Okay, again, but that examples the in operator, something that I also look at that the instance of assignments, control flow analysis, using types predicates. Okay. Which is something that we're gonna see in today's video. So this is what it is, right? This value that I'm going to pass here, right? It say, hey, what is the value of this, right? So I can say that, hey, this is now unknown because I don't know actually what this value is, but I do want to coerce that into this strings array, right? So, but the whole point of this type guard, which is checking a value against it is type of checking a value against it is type of value, right? Here, I'm checking against the value return a type of like this. All right, this is what I'm doing here. And checking the type guard, and they call type guard because anytime that you want to check against a value returned by the type of, you are doing a type guard. Okay, part of the lingua franca. Okay.
The solution here is amazingly simple. This used to be a much more complicated problem to solve, but since TypeScript 5.5, which as of time of recording is just been released, we can now do this. I can just copy this logic into here. I can say const is array of strings, and then I'll just return this value here.
I put it
obviously we're getting some errors because value is not defined, so let's define it here, saying value is of type unknown. And now I can just replace the logic inside here and just say is array of strings, calling it on value. And it works. Now this is amazing to me. I mean, to you watching this in the future, this might not be so amazing because TypeScript will have had this for a while. But what's happening here is if we hover over is array of strings here, then you can see that we have the function parameter just there. In fact, I'll zoom in a touch. And we have a return type here, which looks very interesting. We have value unknown as the parameter, and the return type is value is string array. This is what's called a type predicate, and type predicates are something which are quite advanced in TypeScript. We will look.
Type predicates. Type predicates. Yeah, they don't mention anything like that. Type predicates. Instance of control narrowing. This is just for narrowing. Type predicates here. So we have worked with existing JavaScript construct to handle narrowing so far. However, sometimes you want more direct control over how type change throughout your code. They use the define. Okay, more control about how the type change here. To define a user defined type gar, right? Not those returning by type of. We simply need to define a function whose return type is a type predicate. In this case, it's like this. Pet is fish. So whether it's a fish or a bear, right? And then I want to do is this. If pet is a fish, pet is fish. So it's gonna return is a fish. So it pets as fish. Then I'm gonna check for the swim property, and if that exists, give it to me. All right, give it to me that or saying evaluate this expression and say, hey, this is fish. Pet is fish is our type predicate in this example. A predicate that takes the parameter name is type, where parameter name must be the name of a parameter from the current function signature. Anytime a fish is called with some variable, Typescript will narrow that variable to that specific type if the original type is compatible. So here what we're doing is now, hey, if I do have that, all right, and I'm going to narrow that. Oh, here what you're doing is like type predicates with duck typing. Why duck typing? Because you're saying, hey, if this has this property, so if this sit like a dog, walk like a dog, fly like a dog, so there must be a dog here, right? Okay. Type predicates here. Anytime is fish is called with some variable here, Typescript will narrow that specific to the specific type if the original type is compatible. So if this is fish, it's going to narrow down to a pet or into a bear here. Notice that Typescript not only works that pet is a fish in the if branch, but it also knows that in the else branch you don't have a fish. So you must have a bird. You may use this type gar is fish to filter an array of fish and birds and obtain an array of fish by saying this. Hey, I am defining here is a value that I'm going to pass is now get small pet, and get small pet. So it's functions, your functions call, right? And even in your SU, you say, hey, I'm gonna call this is fish. So I'm gonna call each one of, so I'm gonna verify if that is a fish in our SU, right? So I just want to get only the fish, all right? And the same for this as fish, right? The predicate may need repeating for more complex examples. So for example here, su.filter. So now instead of passing is a function like this is fish, I'm going to pass is now a predicate to verify that, right? So hey, this pet is a fish, right? And it pet.name is equal to Sharky and return false. So I want to exclude now this one. In addition, class use this is type to narrow their type. This base type gar. This base type guard. Okay. This base type gar. Okay, this base type gar. So here I'm creating is this class, and this another class that extends for that. This another class, and this networker. And here I'm gonna create this and say, hey, if this is a file, And here I'm saying is this is file. Okay, to verify is the constructor, to verify is this property of the function constructor, and then return this instance of file rep. And it's going to verify is okay, and it's going to check if this object is this, and again this is a value from functions, and I'm going to verify if this function is an instance of a file rep, or in this case I'm going to verify if this class here is an instance of the file rep. If it is, all right. File rep, whether it is file, is directory, or is network. So whether it is file, and checking if that file, hey, that it must contain is the content as it is, right? Or host or children. Else if this is directory, so give me the children's. Okay. Else if this is network, give me the host. Okay, this is for more advanced. Okay, this is for more advanced type guards, predicate type guards. Okay, but let's go into this.
Look at them, I think probably in maybe the last chapter of this. And what's going on here is that Typescript is inferring the fact that we're returning this logic inside here. We're doing some narrowing inside there. And it's inferring the fact that this function, when it returns true, will mean that value is inferred as an array of strings. So when we call it on here like this, it means that value is an array of strings. If we were to do the reverse, if we'd say it's not an array of strings, then value inside here would still be unknown. But outside of those brackets, value would be an array of strings. So it's like we're able to recapture some of this narrowing logic, put it inside a function, and it just works. You are, of course, allowed to add your own to here. And actually, one thing you'll notice is if you add a return type here, if you add Boolean as the return type, then everything actually stops working. If we hover over this, we can see value unknown returns a Boolean. And because it's not returning any special awareness of what value is supposed to be here, it means that value is still unknown here. So this is a good argument for actually not annotating your return types, because if you're adding this interesting narrowing logic here, then your function is going to be automatically inferred as a type guard. Really, really clever stuff.
That is great, especially when you want to verify for a particular type. All right. Useful if you're going to represent a new shape of that data in that system, usually for APIs or for pulling that, which is something that I'm going to do here in part of the job, is that I'm pulling is a certain set of fields, right? Because those fields are constantly changing to the real estate business logic. So at least at the beginning is this, and then 6 months later it'll be that another one, and so on and so forth. Type.
In this exercise, we have a type called shape, and this shape type has a kind attribute, which is a string, which is always defined. And then we have a radius, which is possibly defined and is a number, and then side length, which is also maybe defined and is a number. Then we have a calculate area function below. This calculate area function takes in a shape, which is a type shape. And we say if shape.kind equals circle, then we return math.pi times the radii, and then we're good to go. We're off to the races. And then otherwise, if it's a shape.sidelength, we assume it's a rectangle instead, and then we just times the shape.sidelength times shape.sidelength. So you can imagine this is a kind of polymorphic function which takes in two separate shapes. And we've got some tests down below. We're expecting the test to pass if we calculate the area of the circle correctly. So this type annotation, though, is really bugging me, because we can actually pass in a bunch of illegal stuff into here. We can say calculate area, and we can pass in like kind. We can first of all pass in like a kind that doesn't exist. We can give both a radius and a side length, which just should not be possible. There must be a better way that we can express this logic. So I'll give you a clue. In fact, I'll give you two words. Discriminated unions is the thing you need to look up. And by doing that, you're going to discover a really interesting way to describe this shape property. It's going to use the union symbol that we've covered before, and it's going to also test your knowledge of narrowing as well. Good luck.
Discriminated unions here. And discriminated unions here. Contextual is similar to Haskell's. Contextual typings. Okay, discriminating unions here. Typescript for functional programmers. Okay, discriminating unions here. Whether it's of this or this or this. The closest equivalent to data is an union type with discriminant properties, normally called discriminating unions in Typescript, because this shape can be either this or this or this. Discriminating unions. Oh, okay. And they call discriminating unions because you can now pass a polymorphic shape to this function. And by I say shape is the value of that argument, or the shape of that argument. For functional programmers. Holy hell. So in other words, I can say something like this and say, hey, so the shape can be either or this. Okay, this is if you're gonna pass some polymorphic shapes. So not only that, it can be sometimes it's either this, all right. It's either kind here or exactly. So if this is a kind, so if this is kind is now, for example, circle, right? It will only have is radius as a number, right? However, if this kind, this is just to be explicit about it. So if this kind is now a rectangle, right, it won't have radius, it will have now the side length here as a number. So this is I'm talking about is discriminating values here. Okay. Sometimes this is what you need in order to solve something or to calculate, to compute something. Okay.
If we think about this shape type, you can see that really we're only meant to call the calculate area function with two different types of shapes, either a circle or a square. And you can see that that's borne out by the way that we're calling it down the bottom. We've either got kind square or kind circle. So we can technically kind of like sharpen this up by using literal types too, right? We can say kind circle or square. And we're doing okay here, but we've actually not gotten that far, really, because you can still pass a square with a radius, you can still pass a circle with a side length. That's not great. What we need to do is we kind of need to split these out into two separate kind of objects, and that will give us the things that we need. So if you think about it, let's actually just define a type square, and type square is going to have a kind of square. And it's also going to have a side length property. So let's just move this down to here. Now this square, if you just think about this type for yourself, that square now has a side length which might be defined? No, that's not right. Side length, if we have a square, it's always going to be defined. You can't have a square without a side length, even if it's 0. It's never going to be undefined. And this shape now, that's no longer just a shape, it's actually a circle. And the radius, again, you can't have a circle without a radius. So let's make that defined too. So now our shape type down the bottom here, this now no longer has a type. So let's actually just say a shape is a union. It could either be a circle or a square. And now we've found our solution. You notice now all of the undefineds have disappeared. We're now certain that if the kind is a circle, it's going to have a radius. Otherwise, it's going to be kind square side length number. So let's take a look at our function. Our function now is saying calculate area shape shape. And if we say shape.kind equals circle, you can see that kind is either going to be circle or square, then what we get is shape.radius is now defined. And if we hover over the shape inside our function that calculates the area, you can see that it's been narrowed down to circle. What? Then inside the else scope just here, we have shape.sidelength, and we can see that inside there it's square. Amazing. If we were to move shape.sidelength out, and in fact let's just sort of like remove a couple of these return statements, you can see that only inside the proper scope where it's narrowed is our narrowing actually being applied. And just by checking the kind, we can also check the other parts of the union. This is what's called a discriminated union. And you'll notice that a discriminated union always has basically a discriminator, the thing that's in common between all of the types that are part of it. So in this case, we have two object types. We have square, we have circle, and the shape is the discriminated union. If we removed kind and we made one of them type like this, then the whole thing breaks down. There's now actually no properties in common between circle and square, and so if you to just check shape like this, we're not getting any autocomplete because there's no properties in common, meaning that any property we access is not going to like us, it's not going to be happy. So if we change back our type to kind, now there's one property in common, which is kind. And now we're going to get kind on there, meaning that we can check it in an if statement to check which branch of the union we're on. And of course, discriminated unions can have other properties in common as well, but there's always one discriminator that's usually the one that's used to check if you're on one branch or the other. So this is a discriminated union. It's so useful in so many different situations. It's quite hard to get your head around. And the fact that it takes in literals and like narrowing, and also takes in union types as well, it means it's a really powerful, pretty advanced way to use TypeScript and build out the sort of shapes of types and the APIs that you want.
Mainly on the APIs, man. Because look at this. So I'm just recap all the things that I have saw, and that is especially when you have a functions that is receiving arguments, and these arguments change the shape. So it is polymorphics, or in other words, you are computing is based on specific scenarios. So in those cases, when you have now a function that has some shared properties, all right, it makes sense for us to say, hey, let me now is create a particular type for the scenarios and another type for this another scenarios, and then combine that and use that as a union discriminator. So in other words, I can say this is now circle, and the discriminator property, which is using now a literal called here circle, right? And then you have now what are the specific things that this type has. Particularly is radius. But if you have now a rectangle, for example, rectangle type, and here you say rectangle type, so you don't have a radius, you have now the side length in this case, right? So, and not only that, but when you want to now combine is the shape of this, whether it's you use is or combine or union, whether it's the cycle or rectangle here, right? And then I want to take down here. So this is the idea of this notions. This is side length. I misspelled that. Side length. This is the notions of the idea behind narrowing and wideness, right? Or union, right? And this is the idea of playing now with Typescript essentials here, especially to describe is different states of your systems. And this is so useful to use this to discriminate that. And that's quite interesting because this is reading about the Typescript for functional programmers. Unlike Haskell, the tag or discriminating is just prototyping. It's just a prototype in each object type. Each variant has identical property with a different unit type. This is still a normal union type. Deleting here is optional, part of the union type syntax. And you can discriminate the member of union using normal JavaScript code like this. And of course, it's using now the same example as it is. Note that the return type of area here, right, is inferred to be number because Typescript knows the function is total. In some variants, here is is area. Is area exactly? It's a number. So if some variant is not covered, the return type of area will be number or undefined instead. So also, unlike Haskell, common properties show up in any union. Haskell. So you can be useful discriminating multiple members of the union. That's interesting. Haskell. All right. Chill. Chill. The structuring and discriminating.
We're starting from the solution for our previous exercise. This calculate area function, which takes in a circle or a square in the shape of a shape, discriminated union. And except though we've changed something about it. Instead of it being just shape here, we've really, inside the function parameters, we've instead changed it to be a destructured kind of like object here with kind, radius, and side length destructured from the object. Now we're doing our usual checks here. We're saying if kind is circle, but we're getting some errors. And we're getting an error saying property radius does not exist on type shape. Your job is to try to work out why on earth that error is happening and how we can get this destructuring behavior without compromising any of our code and still making all of the tests pass below. Good luck.
I think is that by looking at the radius here does not exist in shape. All right. So what I can do is to say, hey, whether if I be explicit about this or by saying, hey, if the radius is the radial property in square or in circle, right? In circle, let me in fact go to the structuring and discriminating union type. The structuring, exactly. So the structuring and discriminating union union problem here as it is, right? So I do have this. I want to know what can I do here and what are the possible solutions that you offer with the quick fix menu. It's an infer return function. You say this infer return function. Okay, it's not infer return function, not at all. You're not helping me here. And if I go and I hover here, say property radius does not exist on type shape, right? Trying to access radius of an object that doesn't contain this. So how can I make sure that you contain that, right? Whether if I say, because this is now union type, whether if I say kind, unless I say something like this, whether if I say hey Typescript, this is the length of this, but if this is a circle, right, or if this is now in a square here, so something sometimes, so combine things like that, right, where I'm saying, hey, this is like circle, right, and otherwise I will have is this as it is. Do you accept this? Or am I just being wonky here with this, right? Shouldn't just accept that, right? Because it's a shape. So if I want to narrow this here, so what I will do is, if I am the code, I will say, hey, this is radius, right? If I am the code, I say, hey, this will be the radius, and I'm going to check that and say like instance of the shape, right? So this is the syntax of the shape. So now I make sure that I have is the the circle here. Now I make sure that I have is the property radius. Radius is an instance of circle, but only refers as to a type, but it's being used as a value. Oh, so you say the type of, so if radius is type of circle, right, it will say, hey, no, and circle have no overlap. So you're right, because I'm checking is now is that. So the thing here is that I do want to check for this value as it is, right? But at the argument level, here at the argument level, we know that it has kind circles, but radio does not. So somehow, can I say something like this? So I'm not sure if I can say something like this, especially at the argument level. And that's interesting. That's interesting. So what if I want to the structure in this? I can say either is a circle, all right? And it say, hey, that's right. So if this is a circle, it can be this. Or if this is now a square, but it say, hey, square does not exist there. So what I can do is perhaps using the optional thing here. Okay. Binding parameter cannot be optional in an implementation signature. Binding element radius implicitly has an any type, and it cannot bind that. Cannot be optional in implementation signature. Okay, so it cannot be optional. All right. Property radius does not exist. Shape. So if I want to combine here, I'm quite lost here of how to do this.
Okay, so the weakness of
destructuring union types. Destructuring union types. Let me look at this. Right, the structuring union type. The structuring. The structuring here in array, tuples, and objects like this. Because at the end of the day, this is an object. I'm destructuring that object here. Destructuring union type. This is some variable declaration. Object destructuring. Union destructuring, particularly. So union destructuring. Destructuring. Working with union types. This is now everyday types. Working with union types. And destructuring. Exactly. This is for these simple cases. But what about the objects? And destructuring union types, right?
Discriminated unions really is that you can't really destructure with them. You can in certain ways, but certainly not in this way. The reason you can't do this is because if you think about it, the moment that this is passed in, the shape is passed in, we don't know if it has a radius or a side length yet. So technically TypeScript could get around this and say, okay, side length is undefined here maybe. But really what TypeScript just wants to do is give you the kind property, because that's the only one that's in common between them. So this rather confusing error, property side length does not exist on type shape, what it's really saying is property side length does not exist on all branches of the type shape. So if we remove those,
on all branches,
and if we say, okay, what we'll do is inside this, let's say we get our shape back through our sort of a rest parameter in destructuring, then inside our first branch of kind equals circle, we can say, let's just destructure again, and we can say const equals shape, const radius equals shape here. But now this is a little bit annoying because kind inside the function parameter has been separated from the rest of the shape. It's no longer a property of shape, it's actually just been pulled out. And so TypeScript can't quite track the relationship between kind and shape. Oh no! And so the destructuring here, property radius does not exist on type radius number or side length number. So it can't quite tell the difference. So the best way to do this, I think, is just to give up destructuring inside the actual body of the function, inside the function parameter, change that back to shape, and we say if shape.kind equals circle, then inside this branch we can now say const radius is shape. And now everything works, because what we've done is we've said, okay, the narrowing is applied to a property of shape. That means that shape is properly narrowed down to be a circle, as we can see from the hover. And that means we can, inside our function body, we can pull out radius. It means you don't have to kind of like grab something from our function property or object property. And we can do the same thing down below with the other branch, and we can say const side length equals shape. And now everything just works. So this, I think, is the easiest way to do it, is to apply your destructurings closer to where they're actually used, or do what I do, which is not actually destructure that much when you're using discriminated unions. And in fact, I find myself not destructuring very often. Certainly destructuring objects very often at all. I tend to just prefer actually just grabbing the properties and just sort of put them on. I don't mind lots of dots in my code, that's absolutely fine. TypeScript lets you autocomplete, it's all really nice. But if you want to destructure, this is the best way to go.
So the structuring discriminated type, union type. Okay.
We're back here with our circle and square setup with our calculate area function, where we're still checking to see if math.pi is the right shape and we've got the right radius, and we're still handling squares too. We've got our discriminated union at the top. Nothing has really changed. We're not doing any of the destructuring that we were doing before. It's all the same. But I want you to refactor this code. I would like you to refactor the calculate area function, just the stuff inside the function body, to use a switch statement instead of an if-else statement. This, I think, is going to make this thing a lot easier to maintain going forward. When we add, like, let's say we need to add 20 or more shapes. We want this to be easy to extend, and currently this if-else statement might get a little bit unwieldy, and it feels like the shape.kind equals circle, shape.kind equals triangle, shape.kind equals whatever. That's going to get a bit tiresome. So your job, figure out how to refactor the code inside the function body to use a switch statement instead, while still preserving all the behavior and also investigating how TypeScript narrowing works in that switch statement. Good luck.
Exactly. It's like now taking a look at, this is the structuring, how the structuring is not useful for discriminating types, all right? And if you have to do that, well, try to extract them at the narrowing level for doing so. So that makes quite sense. And here's we're using is now with the switch case, right? Switch case here with using type predicate with this narrowing. Okay, using type predicates in narrowing on this switch, switch like this. So instead of doing this, why do we want TypeScript also use switch statements and equally check like double equal. Okay, for this comparison to narrow types like this. Yeah, but it doesn't give me any example with that. Switch like this, discriminating unions. Oh, look at the discriminating unions here on narrowing. Okay, so discriminating union on narrowing. If I go here, right, if I go here and say discriminating union with narrowing, I'm gonna say, hey, depend of the switch case, which is here, and by default is this. Oh my god, I have a lot of time without using a switch switch case. Exactly. Yep, let's get into this. So depend of the use case here of the shape dot kind, right? So if that is the case, in which if I use now the autocompletion feature, no, what the French do you think you're doing? It actually gives me that, which is something that I love about this. Hey, well, let's go into now is return this statement here. But now if the case is a if the case is a rectangle, you can actually take a look at that, or square, rectangle, square, well, you get the idea. So now I do want is to do these computations instead, right? I can also handle is the case of default, right? Default, right? To actually, if I receive something, I'm gonna return nothing. But I don't want to deal this scenario here as it is. So this is how you can actually is narrowing with union discriminating. So in other words, I can say is, hey, if I am just structuring here the kind and the side length, what I can only do is here with the kind, okay, depending on the kind I will need to access is to that, and here it will not automatically tell me what radio is, but here inside of this statement I can do is something like, hey, let go to the, well, in this case, as you can see, that's actually is not quite accurate, so it's preferred for this to go with the shape in mind, you know, and that is way much more easy to work with that.
Okay, let's check out this calculate area function. We can remove all of this code. As soon as we remove it, all of our tests are going to break. But let's add a switch statement in here. And we're going to add shape.kind inside here. And now a couple of things happen. First of all, we get a case. And you notice too, we're going to get autocomplete for case circle here. Look at this. So case circle, and we've got case square too. So TypeScript understands that shape.kind could be circle or square, so we get this gorgeous autocomplete for this, which is just below here, case circle. And so nice, and that's going to happen if you have 20, 40 members of your discriminated union. So we get case circle, and now we can return the code that initially figure this out. So I'm going to just sort of skip over some code here, and we get to this point here where we have case circle return math.py shape radius and shape radius. And this is really cool. If we hover over this too, you'll see that our function always returns a number. Isn't that clever? So if we were to remove one of these or comment this out, you'd notice that we get number or undefined. But TypeScript understands here that we have shape.kind, which can either be circle or square, which means that any value passed into this, as long as it's a value of like a valid kind, is going to hit one of these branches. If we were to, let's say, just return or not return one of these, you notice that we don't get a fall through here unless we do first of all, the thing we get back is always going to hit the square thing here, which doesn't seem right, but we can add a break inside here to make sure that it actually breaks, because otherwise inside square we would see something that's either circle or square. How clever is that? It understands all of the ways it can fall through. Gorgeous. But if we add a break here, of course that's not going to happen. And if we add a break here, then this is going to be number or undefined. So TypeScript is so good with discriminated unions and switch statements. The final solution here is to have a return there and a return inside here. Of course, we don't need to add these curly braces here, but we can if we want to. It means we can add like a multi-line code block in there. This works perfectly fine too, but lovely. So discriminated unions and switch statements are a match made in heaven. Another pattern that you might be used to with switch statements is a switch true, which is kind of like a if statement, but can be kind of molded into a switch statement. So what we're saying here is switch true. That's interesting. And then the thing that we pass into the case here is actually going to be the thing that we're checking to check if it's true or not. So sort of counterintuitive way of structuring your code, but it can be really, really useful when you have complicated sets of logic that you want to kind of fall into each other. So we've got our calculate area function. Our calculate area function has the same kind of checks as it has before, but you notice here that it's still working even if we've got switch true. So we've got case shape.kind equals circle, very clever. Then it gets narrowed properly into circle, and shape.kind equals square gets properly narrowed too into a square. Beautiful stuff. This has actually only been possible since TypeScript 5.3, and you might be reading this or watching this in the future. Currently this is on the beta version of TypeScript, which is coming out, so you can see how TypeScript kind of evolves through time and adds these kind of new changes, which is super duper cool. But anyway, this is switch true. Also works really nicely with narrowing statements like this, or discriminated unions like this, and with other kinds of narrowing too. Very cool.
For narrowing things using the switch statement here.
In this exercise, instead of talking about a discriminated union of objects, we're going to look at a discriminated union of tuples. We have a fetchData function, which is an async function which returns a promise containing an API response. And this API response is a tuple. Now that tuple currently has two members. The first member is a string, and the second member is an array of users or a string. And let's kind of look and see what we mean by that. The first way that this tuple can resolve is basically by having, we have a tuple which contains error as the first member of the tuple, and the second is a string containing the error that occurred. Then down the bottom here we have another one which is success, and that then returns the data. And you can start to see that we've modeled our API response a little bit inaccurately. We have kind of several possibilities. We can pass stuff into this API response that isn't error or success, and we can do the wrong combinations too. So we can pass in an error when we're in fact returning the data. So your job here is to figure out how you can change the type of this API response to be more accurate, probably using a discriminated tuple or a union of multiple tuples. And then inside the example func down the bottom, we want to check that this is working. And you notice that when we fetch the data, here we fetch the data and we get back status and value. We want to check if the status equals success, we want to console log the value, and we want in that case the type of value to be an array of users. Otherwise we want the value to be a string here. So that's your job. And this is, I think you'll have all the pieces you need to understand this and get it right. And notice as you're going through it how TypeScript is narrowing and the clever things it's doing. And I'll see you in a minute.
Again, the whole point here is by exploring is the narrowing in union, right? Because we want is to now represent is now a set of possible combination here. I can say is API response. You can say is a type here. By saying is instead of API response, I can say is well, there is type success response. Might be quite long, and the other is a type error. Okay, and I can say it's just something like this and say, hey, this will be called now success and this will be called now error. Okay, and here what I can say is to combine in this tuple these two types, whether it's success or error here, and then now do some things like this. So if you don't have a response here, so now cleverly so now cleverly it say, hey, I need to return is either is a success or an error. This is the type of this, and if this is now an error, which is part of the API promise here, okay, this is the API response. It can be received as an error or success, and here what I do want to check if this, right, you say, hey, is returning is now the value, but it can be the string or a user. But if this is a success, right, so if this is a success, okay, so look at this. I can either say something like this. So if this is a success, you will return now is a user as it is, right? Or now using the union discriminations to say this is to cover another scenario. It says error, and you're going to return now as a string here, right? And that is marvelous because now this response actually say this, hey, it can be this a scenario or this another scenario using the union discriminating here, right? And this union discriminated, they going to not necessarily have things in common here, but here you can now think of this like the specific type in this scenario, and this is another one on the success on an error. Holy moly, bro. Okay. So the idea of this kind of exercise is to explore more about is this concept of first assignability, all right, in your type assignability based on unions, based on wideness types, or narrowing type, or this notion of wideness and narrowness. That's the whole point of this. Okay, it is quite powerful to cover these scenarios here. It is quite powerful to cover this scenario. Hey, in this case, I would like to return this, or in this another case, is this one.
Okay, so API response now. We need to split these out into two separate states, two separate possibilities, because currently it's too wide, it's not helpful enough. So let's do the error state first. Let's imagine that instead of string, we now want to say, okay, one of the possibilities here is you return an error and then the string that comes with it, which is the message. Okay, nice. But now we're getting an error here saying success is not assignable to type error. Well, we can add a member to this discriminated union. And this is a discriminated union where we have success in the first one and then an array of users in the second. The discriminator is the first member of the tuple. So we have either the first one being error or the first one being success. And the first member of the tuple then defines the second member of the tuple. So error, string, success, user. And now everything inside the function works really nicely. So we're getting we have proper results here. So if I try to return an array of users inside here, it's going to error because, first of all, it says, oh my God, it's saying a bunch of different horrible stuff. Oh yeah, of course, because I'm actually trying to write some TypeScript in a JavaScript slot, so that wasn't good. So we have type empty object is not assignable to either of the possibilities here. So imagine if it was just an empty array, then we would get an error here saying type at position 1 in source is not compatible with type position 1 in target. So basically type this array is not assignable to type string. String is the only thing we can pass in this slot. But how about down the bottom? Because down the bottom, you notice that before we talked about destructuring indiscriminated unions and how you can't do it. Here we're destructuring, we're using an array destructurer, pulling out the status and the value. And you might think in these situations, well, status and value, they're totally unrelated to each other. They're pulled into two separate variables. But TypeScript actually, with tuples and with discriminated tuples, it keeps track of that relationship. So if you check that status is success, then value is actually narrowed down by relationship. What? How cool is that? This works for discriminated tuples, not discriminated objects. I don't actually know the reasoning for that, but this is how it works. And then on the
this is work for tuples.
What? How cool is that? This works for discriminated tuples, not discriminated objects. I don't actually know the reasoning for that, but this is how it works. And then on the else branch here, then value is going to be string, and everywhere else it's either string or user. So cool, so clever. And it's actually a really nice use case for discriminated tuples. It's cool that TypeScript lets you do this, lets you return kind of like a double from your function in this way, lets you pull them out into different variables, and lets you kind of narrow them based on the value of the other. Very nice.
That'll be all for this video. Take care. Bye-bye.